Dear students, we have already started the second semester topology paper. That is, we have started with the compactness in matrix spaces. And today I am giving the first video on compactness. And there are 7 pages for this particular notebook. And we'll discuss it in detail. We start with the T1 spaces. A topological space X2 is a T1 space provided that for each pair xy or distinct points there exist open sets uv such that x in u, y not in u, and y in v, x not in v. The figure is given there. And the x and y are distinct points and there are open sets u and v containing them in such a way that x in u but y is not in u, and y in v but x is not in v. And there are remarks are given. Every T1 space is a T0 space, every T2 space is a T1 space, every matrix space is a T1 space. A T0 space need not be a T1 space. We can give an example for that. Say, take x equal to 1, 2, 3 and tau equal to x5, set 1, set 2, set 1, 2. x2 is a T0 space but not a T1 space. Because for 1 and 3, two elements you are taking x, set 1 is an open set, such that 1 is an element of set 1 but 3 is not an element of set 1. But that does not exist an open set containing 3 and not containing 1. One theorem we are discussing. Let x2 be a T1 space, let A subset or equal to x, and let P be a limit point of A, then our neighborhood of P contains an infinite number of distinct members of capital A. We will discuss it with the proof. We prove the result by the contradiction method. If possible, assume that there exists a neighborhood U of P which contains only a finite number of elements of A. This implies U contains only a finite number of elements of A other than P. Okay. Let these elements of A be, you can take a x1, x2, etc. xn. Now P is already there, so P is there and xi in x for I equal to 1 to n. So now P xi in x and capital X is a T1 space. That means by definition there exists an open set ui such that P is an element of ui and xi is not an element of ui. This is true for I equal to 1 to etc. n. So we take u intersection all other u1, u2, etc. un. So u intersection, u1 intersection, u2 intersection, etc. intersection un is a neighborhood of P which does not contain an element of capital A other than P. That means P is not a limit point of capital A, which is a contradiction for our assumption. So our assumption is wrong, hence the theorem follows. Next page, and definition we start with let theta be an open cover of a metric space XD. We are discussing Lebesgue number. A Lebesgue number for theta is a positive number epsilon such that each subset of capital X of diameter less than epsilon is a subset of some member of theta. That is what the definition for Lebesgue number. Theta be an open cover of a metric space XD. A Lebesgue number for theta is a positive number epsilon such that each subset of capital X of diameter less than epsilon is a subset of some member of theta. Okay. So one remark is given. A very open cover of a metric space with a Bolzano-Weierstrass property has a Lebesgue number. Definition. A topological space X2 is countably compact. We are discussing, and that is variations of compactness we are discussing. The first one, the countably compactness. a topological space x2 is countably compact provided every countable open cover of X has a finite subcover. So clearly, every compact space is countably compact. Next definition, that is finite intersection property. A family A of subsets of a set has the FIP or finite intersection property, provided that if A dash is a finite subcollection of A, then intersection A is where A element of A dash is not equal to phi. That is, that intersection is not equal to phi. That family A equal to collection of or closed open intervals A infinity, where A is in R and A greater than 0, then A has the finite intersection property. Clearly it follows. Next theorem, statement, a topological space x2 is countably compact if and only if every countable family of closed subsets of X with a finite intersection property has a non-empty intersection. It's an important theorem. You can go through the proof for it. First, suppose that x2 is countably compact. Let A, family A, that is the collection of all such E alphas where alpha in index set, be a countable family of closed subsets of X with the FIP, the finite intersection property. What we have to prove? We have to prove that intersection A alpha where alpha in the index set is not equal to phi. If possible, assume that intersection A alpha equal to phi. We have to prove that intersection A alpha not equal to phi. For that, first we are taking the assumption, that is, if possible, assume that intersection A alpha not equal to phi. So consider this complement, that is collection X minus A alpha, where alpha in the index set, which is a countable collection of open sets in X. Whatever their union, now union of X minus A alpha, where alpha in index set, that's equal to X minus intersection A alpha, where alpha in index set, that is equal to X minus phi, which is equal to X. So what you're getting is collection X minus A alpha, alpha in index set is a countable open cover of X. But x2 is countably compact. That means there exists alpha 1, alpha 2, etc., alpha n in index set such that union X minus A alpha I equal to X. That is, it's a cover. This implies X minus intersection A alpha I, where I varies from 1 to n, is equal to capital X, which implies intersection A alpha I equal to phi, which contradicts the finite intersection property of the collection A or the family A. So we must have intersection A alpha not equal to phi. That is the first part. Now we have to discuss the converse part. Conversely, suppose that every countable family of closed subsets of X with the FIP has a non-empty intersection. What do we have to prove? We have to prove that x2 is countably compact. If possible, assume that x2 is not countably compact. Let theta, you are taking a cover, let theta equal to collection U alpha such that alpha in index set be a countable open cover of X having no finite subcover. Let family A is equal to X minus U alpha where alpha in index set, then A is a countable collection of closed subsets of X. If A does not satisfy FIP, then there exists alpha 1, alpha 2, etc., alpha n in the index set such that intersection X minus U alpha I, where I varies from 1 to n, is equal to phi. That is, X minus union U alpha I varies from 1 to n is equal to phi, or union I equal to 1 to n U alpha I is nothing but X itself. That means theta has a finite subcover U alpha 1, U alpha 2, etc., U alpha n, which is a contradiction. So we must have finite intersection property, FIP. Then by assumption, intersection X minus U alpha, alpha n in the index set is not equal to phi, or X minus union U alpha is not equal to phi, or union U alpha not equal to x, which is a contradiction to the statement, given statement. What is the statement? That theta is an open cover of X, hence X2 is countably compact. Coming to next theorem, every countably compact space has the Bolzano-Weierstrass property, BWP. Every countably compact space has the BWP or Bolzano-Weierstrass property. We are discussing a proof of it, that X2 be a countably compact space, that A be an infinite subset of X. We are taking an infinite subset of X, that is capital A, that B equal to collection x1, x2, x3, etc. be a countable infinite subset of capital A. Now we show that B has a limit point in X, so that A also has a limit point in X. That is the idea. We show that B has a limit point in X, so that A also has a limit point in X. So what we are assuming, if possible, assume that B has no limit point. For each n in n, let Cn, that is collection xn, xn plus 1, xn plus 2, etc., then Cn has no limit point. Why? Because it is given in brackets. If Cn has a limit point, then B also has a limit point. So what does it mean? Cn is closed for all n. Also, what is B now here? B is nothing but C1. That contains C2, which contains C3, etc. Hence, collection Cn, n in n, is a countable collection of non-empty closed subsets of X satisfying FIP. This implies intersection I equal to 1 to infinity, Cn not equal to phi, since X2 is countably compact. Let xn or xk, you take xk, an element of intersection n equal to 1 to infinity Cn. What does it mean? This means xk is in Cn for all n. But xk is not an element of ck plus 1. What is ck plus 1? Collection xk plus 1, k plus 2, etc., which is a contradiction. So B has a limit point. This implies A has a limit point. Why? Because B is subset or equal to A. Hence, X2 has the Bolzano-Weierstrass property.